Okay, so this is the 16th lecture. In this lecture, we're finally going to sort of talk about the elephant in the room, which is the fact that we've only ever discussed uniform probability measures and independent trials of fair games. And in our analysis of probability so far, we have explicitly denied the existence of causality. When we've discussed independent random variables and coin flips and rolls of die, we have always made an implicit or sometimes explicit assumption that one flip of a coin does not affect another, and one flip of the die does, or one roll of the die does not affect the other. And, when we've used analogies like weather, we've kind of done it based on an idea that the weather yesterday doesn't affect the weather today. But as anyone who has observed the phenomena of seasons knows, the weather yesterday does have an effect on the weather today. Um, with the analogies of coin flipping and rolling die, the paradigm of elementary probability, where everything is assumed to be independent, applies pretty well. And that's why coin flipping and rolling die and other gambling games were the historical origin of mathematical probability. It's because gambling games are designed to be unpredictable at a small scale. You play, well, it some gambling games are human on human games like poker, and that's something very different. But a mathematical gambling game is something like roulette, where there's no actual human on human component. You're just trying to beat the gods of chance at their own game. And if you're playing poker, you can work really hard and spend your whole life getting good at poker, but you can do whatever you want to do and you will not get good at roulette. It is impossible to be good at roulette because it is a mathematical game. It is just randomness, and you can try to predict it on a small scale and you'll fail. But what, the point of roulette as opposed to the weather is that if you play roulette over and over again and you have enough money to keep betting and betting, you'll eventually start to discover that this is actually a very predictable game in the long term. It's just a negative expectation game. Like, I don't exactly remember what the expectation of roulette is, but it's negative for the player and it's positive for the house. And if you keep playing roulette over and over again, you'll just find yourself gradually losing money at whatever the negative expectation of roulette is. So, that's what independence does. It makes mathematical analysis of a probabilistic situation very easy, and you can predict expectations, you can predict variance, you can use the central limit theorem, you can use more advanced versions of the central limit theorem, but predicting repeated trials of an independent event is just something that is not really a mathematician's job anymore. It's a scientist's job to figure out what kinds of things actually are independent trials of the same event. But if you have a phenomenon in reality and you have a good reason to believe it constitutes independent trials of the same event, then you should have faith that all of your questions have answers in the literature of theoretical math. Repeated trials of independent events are absolutely understood at extremely deep levels, and, you know, ultimately, if you're trying to analyze independent trials of the same event, you should expect that someone with a faster computer than you will be able to do it better than you. Like, all you can do is just try and compute as fast as you can based on well-known mathematical rules. But computing as fast as you can based on well-known mathematical rules is never really going to give you any advantage or provide humanity with insight into reality other than pushing down tiny little inefficiencies on transaction costs. So if we want to move outside of the casino and start really thinking about reality where things have causal effects on each other, we need to move away from the mathematical paradigm of just hypothesizing random variables to be independent. And what that mostly means is that we need to think about what happens when a certain equation from the last lecture fails. In the last lecture, we were discussing independent events, or independent random variables. And we did this calculation where we saw that if x and y are independent random variables, then the expectation of x times y is equal to the product of the individual expectations of x and y. So that was a calculation we did where we had a bunch of independent, identically distributed random variables, and we said that the expectation of x14 times x3 is the same as the expectation of x14 times the expectation of x3. So we were analyzing independent random variables, and we did a calculation where the expectation of a product came out to be the product of the expectations, and that is general for independent random variables. And if you look at the definition I have highlighted in teal called covariance, the first equality, it says covariance of x and y is the expectation of x minus the mean of x times y minus the mean of y. That's the standard definition. It has a natural theoretical interpretation as an inner product of random variables with mean zero, but the way you actually want to deal with covariance in calculations is the second equality highlighted in teal as a definition of covariance, which is you want to calculate the covariance of x and y as the expectation of x times y minus the mean of x times the mean of y. And, you know, mean in that context is just a way of making the language sound a little better and avoid saying the word expectation over and over again. But theoretical math actually optimizes for saying the same word over and over again, and so if we want to do it that way, we can say covariance of x and y is expectation of x times y minus expectation of x times expectation of y. Or, you know, we can look at it as this equation which is the second definition of covariance highlighted in teal, expectation of x times y minus mu x mu y. And if you recall what I was saying about the calculation we did last time when studying independence, we saw that the expectation of x14 times x3 is equal to the expectation of x14 times the expectation of x3. And so that is exactly saying that the covariance of x14 times x3, the covariance of x14 and x3 is equal to 0. So last time we calculated that if we have a sequence of independent, identically distributed random variables, then covariance of x14 and x3 vanishes. That's explicitly the calculation we did. We calculated expectation of x14 times x3 equals expectation of x14 times expectation of x3. And that example motivates something which is universal for independent random variables. Independent random variables have a covariance of 0. And non-zero covariance is a quantitative way of moving away from hypothesizing that causality just isn't a thing. You can try to understand random variables which are not independent by this number, which is their covariance. That is 0 if they're independent, and otherwise quantifies the extent to which they're not independent and may affect each other. It turns out that in order to really measure this notion of a effect between random variables, instead of dealing with covariance, you need to deal with normalized covariance, which is covariance divided by the product of standard deviations. So this is what's called correlation. So the correlation of x and y is the covariance of x times y divided by sigma x times sigma y. So going forward in this lecture, I'll try and suggest to you that this definition works out very nicely, and if you define correlation in this way, it does in fact produce a very accurate mathematical realization of the concept of effects between random variables. But at the beginning, when you just see the definition, I can't especially push the idea that it's obvious why this definition should capture the notion of independence versus causal effect. It's once you start working with this definition, you start to feel why this is capturing the existence or non-existence of what may be causal effects. But at the beginning, you just have to kind of take it as a formalism and say that correlation of x and y is the expectation of x times y minus mu x times mu y, all divided by sigma x times sigma y, and have faith in your previous understanding that these 5 numbers are something you can calculate. There's 5 numbers to calculate a correlation. You need to calculate the expectation of the product, the 2 individual expectations, and the 2 standard deviations. So we've discussed in previous lectures how to calculate all 5 of those numbers given the joint probability mass function of 2 random variables, or the joint probability density function. And so this is something we can calculate, and going forward we'll see why this is a really fantastic thing to be calculating all the time. Okay, so the first thing that you want to know about covariance and correlation is that covariance and correlation are, in a really peculiar sense, generalizations of multiplication of numbers. So if you keep taking special cases down to a really absurd extreme, you'll find that correlation is just numerical multiplication. And I'm not going to try to follow that chain of special cases where you get back down from correlation to multiplication of numbers, but I'm pointing out that abstractly, correlation of random variables is a generalization of multiplication of real numbers, and because of that, correlation works with addition and multiplication kind of like you expect just expanding products. So you have this formula for expressing the covariance of or correlation of a linear combination of random variables by a four-term expansion, which is the generalization of the high school FOIL method. So, FOIL is a method for multiplying two sums. You have x plus y times z plus w. Or I think a better analogy in this context would be, let me just write it here. Okay, so you can see what I just wrote is the numerical FOIL method, and what we see in covariance and correlation is that you can expand covariance and correlation just like numerical multiplication, where you pull out scalars and leave random variables inside things, and then just take individual covariances to reduce this sum of covariances you had down to simpler things. So the point about these formulas, which are analogs of the FOIL method, is that knowing the individual covariances between random variables tells you everything you could possibly want to know about covariances of their sums and scalar multiples. And the same thing is true about correlations. So, we can understand that covariance and correlation are determined by pairwise correlations between random variables, and addition and scalar multiplication on top of that is nothing new. It's just, if you add random variables, you can break their correlations down into individual correlations. And if you multiply random variables by scalars, you can break down their scalar multiples as scalar multiples of individual covariances. So the message from this page is that covariances of random variables matter, and anything with a sum or scalar multiple is just kind of fiction that can be disregarded by expanding until you only see covariances of random variables. So the covariance of two random variables is something that is common and often calculated, and in order to calculate covariances and correlations of sums, you just need to expand like FOIL and then do the individual calculations for pairs of random variables. Okay. So, I want to talk a little bit about the conceptual interpretation of mathematical correlation, which is one of the most subtle aspects in all of data science and probability, because there is a well-known saying that correlation does not imply causation. There's even a joke that I used to think correlation implied causation, but then I took a statistics course, and now I don't think that correlation implies causation, but I have no idea what that has to do with my taking a statistics course. So if you think about that joke, it's supposed to make the point that just because something happened at the same time as something else, there is more to an empirical causal relationship than mathematical existence in the same time and same place. But, you know, causality is something that is appropriately studied in fundamental physics based on notions of light. However, correlation is something much simpler that is accessible to any context with a lot of data. And so, you know, the extent to which correlation actually does imply causation is metaphysical, but the fact is, when people try and understand causal relationships, what they do is look for mathematical correlations and go ahead assuming correlation does imply causation unless you have a reason to think otherwise. And all that ever happens when correlation seems to be different from causation is that, well, you're just looking at the wrong information. So, you know, it's hard to find a situation outside of very deep fundamental physics where a causal relationship is not simply a correlation that hasn't been appropriately interpreted yet. So, I don't know. You have to go around saying that correlation does not imply causation, but as far as anyone actually working with probability, it's like, yeah, correlation is causation, and we have no other way of trying to understand it. So why is correlation such an important measurement? Well, it turns out that you can prove the correlation of any pair of random variables is between -1 and 1. So this gives a natural kind of scale. It's like you have this interval of length 2, which goes from -1 to 1. And what the interval is supposed to say is that positive numbers in this correlation interval tell you that x is very similar to y. And numbers close to 0 in this correlation interval tell you that x has nothing to do with y. And numbers close to -1 in this correlation interval tell you that x has a lot to do with y. It's just the exact opposite of y. It's going in the opposite direction. So the way in which correlation measures effect is with distance from 0. Correlation near 0 is a weak effect, and a correlation far from 0 is a strong effect. And strong effects come in two classifications. You can have strong positive effects, where a change in one variable is tracked by an identical change in the other random variable, or you can have strong inverse effects, where a change in the one random variable is tracked by an identical change in the other one in the exact opposite direction. And what I'm trying to say about changing in the exact opposite direction is that this is perfectly deterministic in the same way as changing in the same direction. It's like, if someone is always doing the exact opposite of what you're doing, there's still a causal connection between your relationships. It's just you move right, they move left, you move back, they move forward. It's just there's still a causal connection, but you have a minus sign. And so that's why correlations near to -1 are indicative of causal relationships. And strong causal relationships have this bifurcation into strong positive relationships where one thing tracks another, and strong inverse relationships where one thing tries to cancel the other. And in the middle of those, you have the absence of causal effects, where correlation is 0 or close to 0, and we think that, well, it doesn't really have anything to say about these two random variables. If correlation is 0, then it's a reasonable hypothesis that the two random variables are independent. So I would say that, observing correlation of 0 is always enough to conclude the absence of causal effect, unless something weird is going on. So usually when experiments show 0 correlation, people think that there's no causal effects here. Causal effects with 0 correlation are kind of abstract and rare, and again involve very extreme situations of fundamental physics which are not generally reflected in reality. So 0 correlation is pretty much a decent analog for no causal effects, as long as you're not staring at the center of a black hole or something. So, okay. So, let's try and have a look at an example where we calculate the covariance. So we want to let x be the sum of two fair die, and we want y to be the number on the first die. And so we're going to try to calculate the covariance of x and y. Okay. So there are different ways. Whoa. There are different ways you could go about calculating this covariance. I will emphasize that if you have two fair die, their sample space has 36 outcomes, and a 36 outcome sample space is amenable to brute force. So there's no actual need to think about this if you're willing to program a computer. So you could just program the definition into a computer and have it compute, and it would do this. But in order to try and get your mind used to it, I'll give an explanation with a little bit of sort of intuitive motivation. So the way we want to understand this covariance is by introducing a third random variable, which is the roll of the second die. And in that case, x is z plus y. And because the dice are fair, we know that z is independent of y. So we can do a calculation where we sum over all possible values of y and z. And when I have this calculation for the expectation of x times y, I have the sum from n equals 1 to 6, sum k equals 1 to 6, n times n plus k, p, y, z, n, k. And if you interpret that, the sum over n is coming from the first die, and the sum over k is what's being added on for the second die to calculate x. So maybe I'll make a small notational adjustment here in order to clarify things even a little bit more. So the reason I switched the order of these factors n plus k and n is in order to emphasize that the n plus k is what's corresponding to x. So I'm summing over all rolls of the first die with the index n. And then I'm summing over all rolls of the second die with the index k. And what I'm getting here is the sum with n plus k for the value of x, which is the sum of the two die, and then n is the number on the first die. So that's how I'm calculating what I get in the equation immediately following the expectation of x times y. And then, as I said, the sample space has 36 outcomes, and there's no actual need to be clever for a sample space so small, but by introducing the roll of the second die, we do get a nice little bit of cleverness where the probability mass function splits up as independence guarantees, and the probability of x of n is just the probability of a specific roll for one fair die, and the probability of z for so the probability of y being n is 1/6 because it's just a specific value of a fair dice. And the probability of z being k is also 1/6 because it's an independent fair dice. So that's why we can turn this joint probability mass function, first of all, into a product of individual probability mass functions, and then just into the number 1/36. And computer told me this is 329/12. So we can calculate the expectation of x in the same way. So this shouldn't be here. So we need to sum over all rolls of the first die and all rolls of the second die to try and calculate the expectation of the sum. So when we calculate the expectation of x, we get 7. And when we calculate the expectation of y, we can calculate by brute force and get 7/2. Or we can say we calculated before that the expectation of a single die is 7/2. We can say that since expectation is linear, the expectation of one fair die is half the expectation of sum of two fair die. The point is we have many ways to calculate the expectation of x and y. So having calculated the expectation of x times y, as well as the individual expectations, we can calculate the covariance according to the requisite formula by taking the expectation of the product and subtracting the product of the expectations. And okay, computer told me this is 35/12. Okay, so now we want to calculate the correlation. So if you remember what we got for the covariance, I have it copied here from example 16.1. We have covariance xy equals 35/12. So 35/12 is the covariance, and you can see that's bigger than 1. And this is the reason covariance is less desirable than correlation as a quantitative measure of effects between random variables. It's because covariance picks up the overall magnitude of the random variable, and you don't really want that. You want to sort of cancel out the overall magnitude of the random variable and just focus on the extent to which they're affecting each other, normalized by the overall magnitude. And so covariance is bigger than 1, and because covariance can be arbitrarily large, it's hard to think of it as a numerical scale. But what's great about correlation is by dividing with the product of the standard deviations to get from covariance to correlation, there's a fact which goes right to the heart of geometry, which is called the Cauchy-Schwarz inequality. And that is why correlation is always between -1 and 1. So we can see here we have this covariance calculated as 35/12. And then we can calculate the variance as we're used to and see that it comes out to be 35/6. When we do the variance of x, we can calculate the variance of y, see that it comes out to be 105 over 36. And we can calculate the correlation according to the required formula by taking the covariance and dividing by the square root of the product of the variances, which is the product of the two standard deviations. And in this case, the answer comes out to be 1 divided by the square root of 2, roughly 0.707. So one way to sort of phrase this in ordinary language would be to say that there's roughly a 70% correlation between the sum of two fair die and the number on the first die. So, it's important to think here, the sum of two fair die is always bigger than the number on the first die. That's just tautological because the second die is positive. But what we're measuring here with correlation is that even though x is significantly bigger than y, the changes in x have a pretty similar effect with the changes in y, and they're correlated in a fairly strong way. So if you get a higher number on the first die, you're more likely to get a higher number on the sum. It's intuitive, if you roll 1-6, if you roll 6 the first time, you're better chances of getting a higher sum. And on the other hand, if you know that you rolled a 12, you can deterministically guarantee that you rolled a 6 both times. So it makes sense that large values of x are correlated with large values of y. Okay, so let's have a look at a final example where we let x be the roll of a fair die plus 6, and we let y be 6 minus the same roll. So we want to calculate the correlation between x and y. So we can see the variance of x. We can calculate according to formulas we've seen before. And we can see that this comes out to be 35 over 12. We can also calculate the variance of y according to formulas we've seen before. Comes out to be 35 over 12 again. And we can calculate the expectation of x, the expectation of y, and we can also calculate the expectation of the product x times y. And in calculating all of these 5 numbers, we've calculated everything we need to determine correlation. So to determine correlation, you need 5 numbers. You need the expectation of x times y, you need the variance of x, you need the variance of y, you need the expectation of x, and you need the expectation of y. And then once you have all these numbers, you can arrange them according to the formula that was shown on the first slide of the lecture. And we can see the covariance of these two things comes out to be minus 35 over 12. And so if I calculate the correlation, minus 35 over 12 divided by square root of 35 over 12 times 35 over 12, I get minus 1, which is supposed to capture the idea that these two random variables are basically the same thing, just going in opposite directions. So, it's like if you tell me the roll of your die plus 6, I can deterministically calculate the 6 minus your roll. And if you tell me 6 minus your roll, I can deterministically calculate your roll plus 6. And the only reason these aren't just the same number is because they're going on opposite directions. So that's what correlation -1 tells you. It tells you that these things are deterministically bound to each other. They change in equal measures, just every change in one is canceled out by exactly the same change in the other in the opposite direction.